Okay, in chapter 3.1, we introduced the differential form for the Maxwell equation, including the Faraday's law and Ampere's Kirchhoff law. They are written as the curl of E equals to the minus of the time derivative of B, while the Faraday's law says that the curl of H equals to the current density J plus the time derivative of displacement current D. So to memorize or to understand the significance of the two equations, you need to notify that to the left are spatial derivative of electric and magnetic fields, while the time derivative are placed to the right of the equation. They are time derivatives. And in the two equations, there shows one source, the electrical current density. And the consequence, the significance of J in this equation is that it's the direct source for magnetic field. And in other words, the presence of a static J, a static current, will not produce electrical field. You only produce the magnetic field. However, if the magnetic field is time varying, if the magnetic field varies with time, the Faraday law suggests that it will produce electrical field in its neighborhood. Similarly, if electrical field varies with time, then it will again produce magnetic field in its neighborhood. So, according to these relationships, Maxwell deducts that there is something called an electromagnetic wave, because time varying electrical field produce magnetic field, time varying magnetic field produce electrical field, and this process can be continuous, so on and so forth, so that the time varying electromagnetic field, the impacts, the effects of the time varying electromagnetic field can propagate as a wave, like a wave, to a distance, to a distant place. So this is the consequence, or this is the significance of Faraday's law and Ampere's Kirchhoff law. So before concluding section 3.1, let's check an example. In this case, we have a current distribution, a current density distribution J. The magnitude is J sub 0, and the direction of the current is AX direction. And it only exists, the currents only exist between Z smaller than A and greater than minus A. So this figure shows the placement of the current density. Let's see. If this is the X direction, positive X direction, and this is the positive Y direction, then the positive Z direction is in this direction according to the right-hand rule. X cross Y equals to the Z direction. So imagine that in our classroom there is this current distribution flowing in the direction of positive x direction, and the currents only exist between minus A to A in the z direction. So you can imagine that there is a war of electrical currents flowing upward in the middle of the classroom. All right? So between minus A and A in the z direction, there is a current goes up in the middle of the classroom. What is the impact or what is the effect of this current war? Well, according to the Ampere's Kirchhoff rule, or according to the right-hand rule of Ampere's law, it will produce which field? Magnetic field, right? Electrical current produce magnetic field. So there will be magnetic field exists in our classroom due to the presence of this electrical currents. And what is the current? What is the magnetic field distribution of this current distribution? Is what we want to know from this problem. So, so this shows the current flowing upward in the middle of the classroom, and if you draw the current distribution along the z direction, it exists only in the minus A to the A direction, to A position. Outside of this region, there is no current density. And this is the answer, but we will see how to come up with this result. And for the meantime, we assume that the current is a steady current, which means that the current maintains a constant value of J sub 0 and a constant direction of flowing up. So using the Ampere's Kirchhoff law in the differential form, we can find out the relationship between the current density, the current distribution, and the associated magnetic field. Now that, because this is the static case, static field case, so the time derivative of D does not exist, so we can just ignore this part, this term. So we have this relationship, and we know that, and the problem gives you the description of Jx, which is J sub 0 Ax. So how do we get Hy? Well, a simple integration along z direction. So you take line integral on both sides with respect to z. And you end up with Hy equals to minus, and it ends up with Hy equals to the minus of Jx on the z direction from minus the infinity to z. And it also comes with a constant. And we don't know the result yet. We don't know the constant yet. Then we can check the result according to the prescribed current distribution of the problem. That is, depending on the limit of, depending on the position of z, if z is smaller than minus a, you end up with nothing, because no current density is included for z smaller than minus a. And if z is between minus a and a, you will get something. And if z is greater than a, you will end up with minus 2 times J sub 0 times a. Why? 为什么? Well, because from the integral from here, because Jx only, J sub 0 only exists from minus a to a. So if z is greater than a, it will end up 2 times a times j sub 0. Okay? So the integrated result of the first term, the integrated result of the first term is actually the blue line in this slide. Okay? So when z is smaller than minus a, it's 0. When z is greater than minus a, it decreases because we have a minus sign in the integral. And when z is greater than a, you have minus 2a times j sub 0. So you have this blue line. So then it comes to the determination of the constant c. Because this is an integration, so in fact you are free to choose the magnitude of c, the constant of c. And as you can see from this result, c is chosen as j sub 0a. Why? Why do we choose c as j sub 0a? Well, so that the answer becomes symmetric with respect to the current distribution. With respect to the current distribution. We know that the current density j sub 0 exists between minus a and a. Minus a and a. So if you assign the constant c as j sub 0a, it will move up this blue line as the blue line will move up and becomes the black line. So it's symmetric with respect to the center, which is z equal to 0. And as you can see here, if you stay in the right of the classroom, you see magnetic currents flows up in the middle of the classroom. And using the right-hand rule, you know that the magnetic field produced by the current wheel in the middle will give you a magnetic field pointing towards this direction, right? And if you change your position to the left, to this place of the classroom, and if you look at the current wheel in the middle of the classroom, according to the right-hand rule, the magnetic field becomes in this direction, right? So depending on your location, the magnetic field produced by the current wheel in the middle of the classroom will exhibit 2 different directions. And this shall comply with the result of the black line. By assigning the constant c as j sub 0a, you will produce a symmetric magnetic field distribution across the current wheel placed in the middle. Okay? So be sure to think about this question yourself. All right, next we can move on to section 3.2, which is Gauss's law for the magnetic field and electrical field, and the continuity equation, which is referred to as what? Conservation of charge in chapter 2 for the 5th Maxwell equation, right? And let's begin with the Gauss's law for the electrical field in the integral form, which is the closed surface integral of the displacement current density equals to equals to the volume integral of electrical charge density.还是把它全写出来吧。All right. So, similar to the comparison of the integral form, you see the first two equations involves closed loop integral of electric and magnetic field, while the third and fourth equation involves closed surface integral of electric and magnetic field. So the third and the fourth Maxwell equation in differential form shall be different from the first two Maxwell equations in differential form. Okay. So again, similar to our derivation of the Faraday's law, we begin with considering a very small volume, As you can see to the top right, there is a cubical region with small size length, which includes delta x, delta y, and delta z. So they only differ from the from XYZ, the point XYZ, by a little distance. So these three little distance, delta x, delta y, and delta z, span a very small cubic volume. In this equation, we see the parameter to the left is the displacement flux density D, which can be written as its projection on the x-axis, y-axis, and z-axis, which are dx, dy, and dz. All three quantities are functions of space and time. So therefore, they have four dependence, including the position x, y, z, and the time dependence t. And so does the distribution of the electrical charge rho, which is also written as a function of time and space. So it's written as rho as a function of x, y, z, and t. The implication of the Gauss's law for the electrical field in the integral form suggests that the closed surface integral of the magnetic flux equals to the of the electrical flux equals to the volume integral of electrical charge density, which is also equals to the total charge enclosed by this small region. All right, let's take another look at this cubical area, which has can be decomposed into six surfaces, six small surfaces. Because this is aligned in the Cartesian coordinate system, we see that the 6 surfaces, including the front, the back, the left, the right, and the top and the bottom surface of this cubical area, which all pointing to different directions. Well, you can say that the front and back are pointing toward the x direction, while the front is pointing to the positive x direction, and the back is pointing to the negative x direction. The left and right are pointing along the y direction. The top and down are pointing toward the z direction. So you simply decompose this closed surface integral into 6 surface integral. And because the surfaces are aligned in the Cartesian coordinate system, so they are not that difficult to write, to express the integral result. Okay, so equation 3.29 states the integral result of the 6 surfaces. As you can see here, the first term includes dx at x plus delta x minus dx as x times delta y and delta z. Delta y times delta z is what? Is the small surface area of the front and back surfaces. dx at x plus delta s and dx at x are electrical flux density at the front and electrical flux density at the back. Because the square region is so small, the planar region surface is so small, we can regard that the electrical flux density is nearly homogeneous at the front surface and at the back surface. So they can be simplified as a product of the electrical flux density at any point in the front minus the electric flux density at and arbitrary in the back on the back surface. And because the two surfaces, the front and back, are pointing to opposite direction, so it comes this minus sign in the middle. Okay, so this is the surface integral of the front minus the surface integral of the electrical flux density in the back. And you can rewrite this equation similarly for the left and right and for the top and the bottom surfaces. So you have 6 surface integral and collected into 3 terms. The question I would like to ask you is this a scalar or a vector? Even though this is written in 3 terms, they are actually scalars, so they can be added together. Why? Because the surface integral is what? Is the dot product, is in the dot product form of the physical quantity, which is a vector, dot, the surface, which is another vector. And the dot product of 2 vectors is a scalar. So the end product of the closed surface integral to the right is actually a scalar. And this result also suggests the volume integral should be a scalar as well. We see for the Gauss's law for the electrical field in the integral form, to the right is the volume integral of electrical charge density law. And because this is a relatively small region, you can see that there's not much difference in the in the variation of charge density. So it can be simplified as a product of charge density within this within a point in this volume times the total volume of this region. That is delta Yx times delta Y and delta Z. And this is the electrical charge density within this region. So you have rho times delta X, delta Y, and delta Z to the right. And if you look at 3.29 and 3.30 together, you can see that you can divide it both sides by delta X, delta Y, and delta Z, and you end up with equation 3.31. 3.31. So to the right is simply the charge density in this region, which is represented by rho, the electrical charge density. And to the left are three differences. There are dx at x plus delta x minus ds at x divided by delta x. In the middle is dy minus at y plus delta y minus dy at y divided by delta y, and so for the z direction, the z component. So as you can see, if you take in the limit, that is to decrease the amount of delta X and delta Y and delta Z to a very small number which approaches to 0, you can write up this equation as this form, which end up as equation 3.32. That is, to the left is del x dx over del x, del dy over del y, and del dz over del z equals to the electrical charge density at the observation point. So you kind of squeeze the small region into a point. Then if this point has a charge density low, then the three quantities in the left of equation 3.32, the difference of dx to its right and left, the difference of its dx, dy, dy, in this two way, and the difference of the z in the z direction. The combination, the three differences, the sum of the three differences should be non-zero, right? Because rho is the point charge, rho is the charge density at this point, rho is non-zero. Therefore, the sum of the three differences should be non-zero as well. Not that comparing to the derivation of Faraday's law, which we examine the difference of dy with respect to z, or the difference of dz with respect to y, the difference are examined in the so-called lateral directions. In this case, we know that we are looking at the difference of electrical field along its field direction. In the derivation of this equation, we checked the difference in electrical field on its sides. So it's referred to as the lateral derivative. 侧向的微分，所以在这个法拉第定理的推导的时候，我们看到这个 curl operation 闪度的操作，它是检视电场这一个场在侧边的变化，而在现在的高斯电场定律里头，你看到那三个式子、那三个成分，它检视的是该点的电场方向，以及这个电场顺着场的方向的变化。假如说这是一个 dx 的话，那这个也是 x 方向。所以它检视的是顺着那一个电场的方向上面的变动， 假如它上面有差异，那表示顺着这一个场的方向是不等的变化是不等于0的。所以这一部分的微分或者这一部分的不是微分，差分啊，称之为 longitudinal derivative。这个字是什么字 ？latitude、longitude 是什么？经度跟纬度嘛。所以你看地球仪里头指的是经度线啊，横的是纬度线啊。所以 lateral derivative 看的是侧边的跟侧边方向那个场的侧边方向的变化 ，longitudinal derivative 看的是顺着这一个场的方向的场的变动量啊，所以在这里头它检视的是 longitudinal derivative, which are the change in electrical field along the direction of the field. So equation 3.32 can be further simplified. In this slide, we try to elaborate the difference between longitudinal derivative and the lateral derivative. Okay, so we see the lateral derivative can be written in the cross form, in the determinant form. So it follows to the form of cross product. So as you can guess, the longitudinal derivative is another form of spatial differentiation, which is operated along the field direction. So it can be expressed in terms of what? In terms of the dot product format. So the longitudinal derivative can be expressed in terms of the dot product format. So it can be expressed as the spatial derivative operator, that is the del sign, dot the field, d, dot the field, which is displacement flux density in this case, equals to rho. So we transform equation 3.32 as the dot product of del operators and the electrical flux density equals to electrical charge density rho. And a more formal name for this operation is what? Is divergence, which is 散度啊，在中文里称之为散度。Kerr 称之为旋度啊，所以上面的是 Kerr of E， 这个嘞，这个要念作 divergence of D 啊。所以它们两个都是空间微分，但是就像我刚刚所强调的，Kerr的这一个空间微分，它是一个 lateral derivative， 所以它去观察的是这一个场的方向的侧边的变化的空间变化，而 divergence 呢，它是 longitudinal derivative， 它观察它所检视的是顺着这一个场的方向的场的空间变化啊，所以它是一个内积的形式，然后上面是一个外积的形式啊，所以这个看起来有点复杂的这个表示式，它经过导入这个散度 divergence 的 operator 跟这个 del operator， 也就是空间微分的 operator 之后，可以被简化成divergence of D equals to rho, the electrical charge density. Okay? And similarly, what is the corresponding differential form for the Gauss's law for the magnetic field? Well, it's It is the analogy. It can be simply expressed as the divergence of B equals to what? Equals to 0. Also, in the formulation of Maxwell equation in the integral form, we have the so-called conservation of charge. 糟糕，有点忘记了啊，偷看一下啊，免得出错。OK， 好啦，所以 divergence of D is referred to is equals to the electrical charge density rho, and this is the so-called Gauss's law for the electrical field in the differential form. So it says that the divergence of displacement flux density at a point equal to the charge density at that point, which can be used to determine whether or not if there is a electrical charge density reside at a specific point. 所以这一条关系是在后面的应用里头可以被拿来做检查，说这个空间中的这一个点有没有电荷的存在啊？那怎么做呢？也就是在你去检查这一个点的电场的 divergence， 或者是电通量密度的 divergence。只要这一个点的电场或电通量密度的 divergence 等于0，那就表示这里没有独立存在的电荷啊，没有停在这边的电荷。反过来，假如你的电场或者电通量密度的 divergence 不等于0，那就告诉你这个地方有电荷的存在啊。所以这是高斯电场定律的一个应用的形式的方式了哈。Alright, so let's try to examine another example. Let's look at this example to see the effect of the Gauss's law for the electrical field. Again, supposing in our classroom, in the middle of our classroom, has a wall made of electrical charge. Not that this wall is made of positive charge and negative charge. So from position minus A to 0, you have minus rho sub 0. So to the left is negative charge. And to the right, between 0 and A, you have rho sub 0, which are positive numbers. So you have positive charge to the right. Look at that picture again. Can it remind you of anything? Well, I bet you have seen this picture in electronics. 你们现在电子学上到电子学1还2了？2了啊，应该一定有看过了嘛。这个是什么 ？P-N junction 啊，对不对？所以在半导体中间的那个 P-N junction， 它是一边是电动，一边是电子，所以它们中间是有那个，你可以把 P-N junction 看作成一边是有带电动的分布，另外一边带的是电子的分布嘛，一正一负的这个电荷分布。Alright, so you have two charge wall. One is positive and the other is negative. The problem asks you, can you describe the electrical field or electrical field intensity or electrical flux density every place in this region? 在这个区域的范围内找出它的电荷或它的电场或者是那个电通量密度的那个分布嘛，分布的描述嘛，And according to the problem geometry, the electrical field established by this this two charge wall ends up with electrical field in which direction? In the x direction, right? In the x direction. And because the wall is homogeneous along y direction and z direction, so there is no difference. There is no difference in terms of the derivative of dy and dz. You only have difference in the x direction for dx. Therefore, the calculation of charge low, or the we only need to calculate the what? dx by integrating using this equation. The electrical charge density is only associated with dx, the derivative of dx with respect to x. So to find out dx, we take line integral with respect in the x direction on both sides. So dx becomes the line integral of low along the x direction, which has a limit from minus infinity to your observation x, plus a constant c. Again, we can determine c at the last step according to the problem geometry. And the problem geometry tells us that the charge density low is placed in this fashion, as shown in the middle of the graph. That is, the charge density is minus low sub 0 between minus a to 0 and positive low sub 0 between 0 and a. So the integral result of this thing is this. If x is smaller than minus a, then you include no charge in the integral. So it's 0 between minus infinity to minus a. If x is greater than minus a, you will account for negative charge only, which will give you a minus number for the dx. So as you can see, if you approach to the center of the wall, approaches to x equal to 0, the dx value will become smaller and smaller, becomes more negative, and eventually reaches the point of minus low sub 0 times a. Then if you moves further to the right, you move into the region of positive charge. Then the electrical flux density that you experience will become smaller. The magnitude of the electrical flux density becomes smaller because part of the effects of the positive charge is cancelled with the negative ones. So as you move further to the right, the dx value approaches to 0 again. Then if you move to a position that is greater than a, the dx value that you experience becomes 0 again. Does that make sense to you? Does that make sense to you? 这个结果合理吗？想想看哦，假如你只有一个带负电荷的墙好了，注意哦，这个墙是往上往下无限延伸。还记不记得我们在第一章里头曾经讨论过一个无限大的带电荷面，它所建立起来的电场？你还记得那个电场的表示是吗？你知道啦，电荷密度越大，那个电场越大嘛，对不对？那点电荷的时候，你发现那个电场是跟 R 平方分之一成比例啊。假如是线电荷的时候，它就跟 R 分之一成比例。假如变成面电荷的时候呢，你就有一个神奇的结果，就是 那一个电场大小是无远弗届的，它跟距离没有关系啊，因为你有无限大的面电荷。所以again， 我们现在有一个无限大的往 YZ 方向延展的电荷墙，所以它所建立起来的电场其实是怎样？其实是我画反了，因为是负电荷嘛啊，所以它是朝内的电场方向，而这个大小会是怎样？无限大的延伸啊，不管远近都是一样大的，好，所以假如你是一个单独的正电荷墙的话，它所建立起来的电场应该是怎样？朝外，然后也是跟距离无关，无限大的延伸，好。所以，假如你把这两个正电荷墙跟负电荷墙所建立起来的场合并起来看，加在一起的时候，你会发现什么？假如你的那个墙的那个电荷的总量，它的电荷密度大小是相同的话，那么在这两道墙之外，这边的正电荷所建立起来的电场跟负电荷所建立起来的电场会怎么样？大小相同，方向相反，所以就没有影响。这里呢，大小相同，方向相反，它也没有影响。所以电场只存在在正电荷之间，正负电荷之间。这是一个想象成无限大的例子。这是一个想象成无限大的例子，但这样的结果其实也存在在很小很小的例子，比如说你电路上面所使用的平板电容，平板电容在充电的时候是不是也是一边是正电荷，一边是负电荷？电容之间一定有电场嘛，对不对？假如你有电荷分布在两个平板中间，请问这个电场会跑到外面吗？会跑到外面吗？会啦，一咪咪啦，这边啦，漏一点点，那种什么霸气外露，它会露一点点出来，这个叫 fringe film。fringe film。不过这个场的比例或者是它存在的范围，也就是那个平板电容外面一点点而已。所以其实无关，不是很要紧啦，你把它忽略不计也没有关系。至于说你在这个电荷的这个电容的上方或者电容的下方，你能够感受到这一个充铆电的这一个电容所建立起来的电场吗？当然是没办法因为在这个电容里头，它的正负电荷的量是一样大的，所以它所建立起来的电场在远离电容的位置以外，就几乎是没有影响的。所以不管是小小的电容或大大的无限大的电荷墙，它所造成的那个效果，其实都是跟这个一样。OK， Alright, so we can, according to the Gauss's law for the electrical field, we can find out the field distribution in this geometry rather simply. Okay, so the solution for this problem, that is the electrical flux density within this region, can be expressed in this form, that is D equal to 0 for x smaller than minus a and x greater than a. And it's a negative value between a and minus a, and they are displaced in a symmetrical fashion. And because the integral results are in symmetry with respect to the x direction, then the constant c can be chosen as 0 because the result is already symmetric, so there's no need to further adjust it. So we can simply set c equals to 0 for this problem. And before we stop, I need to remind you that the divergence operator is also different in the Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system, all right? In the Cartesian coordinate system, the divergence operator is relatively simple. You simply take the vector A's projection on the x direction, which is ax, y direction ay, and z direction az, and taking their derivative with respect to x, y, and z separately, and add up the result because the end product of the divergent operation is a scalar, not a vector. However, if you are performing the divergence in the cylindrical and spherical coordinate system, you need to consider that phi and theta direction, the d phi and d theta are not lengths, they are angles only. So you need to try the length adjustment R or R sin theta so that you can have the correct derivative result. And well, in the midterm problem, I will provide you these equations. So you only need to find out the associated equation you need in考卷的那个有的时候比较佛心，就直接把那个关系式放在考题中间的啦，不然的话就在后面的那个大抄里头了，所以一定找得到的，OK， 所以注意啊，闪度操作在非直角坐标系统里头是要注意那些操作项的，像这个注意像这个。来，以这个为例了哈，以这个例子为例，你在取那个球坐标系统的那个 divergence of A 的时候，在 R 方向的时候，你的修正项是这个R 平方 AR， 但注意哦，这 R 平方 AR 是要跟 AR 一起对 R 微分的，但它还有一个 1 over R to the square， 这个你不要给它拿进去微这要是微完之后再乘上1 over R square 所以要注意一下，这些修正项是在这个微分操作的里面还是外面？里面还是外面？假如在里面的话，它就要参与那个微分操作外面的话就微完之后再乘上去就好了。And examples， 好，我们先休息一下。今天要交第二次的作业哦，交到前面那个袋子那边So example 3.6 involves the divergence operation of vector fields. So you see examples, the A part is the divergence operation in the Cartesian coordinate system, which is relatively simple. You extract the x component of the vector that is 3x and find its derivative with respect to x, so you end up with 3. And the y components, the del dy over y is y minus 3, so it's 1. And the z part is minus 1, so you end up with 3, which is scalar as the divergence operation result. And the second problem is a vector. Vector, which is relatively simple. The vector only have components in the theta direction, and it's related to both r and theta. So it's r to the square times sin theta. And this vector is in the spherical coordinate system, so you need to find out the associated divergence operator of the spherical coordinate system, which you only use the middle one, that is the derivative, finding its derivative along of the theta components along the theta direction. So you need to first taking the derivative of this thing with respect to theta as r to the square sine theta times a theta, which is sine theta again. So you have r to the square sine to the square theta, and taking the derivative of this, which is r to the square sine 2 times sine theta cosine theta, and divided by r sine theta, which is located on the outside of the derivative. So the end result is 2r cosine theta. So I believe that you should be able to carry out this kind of calculation relatively easily. And the last two things we will discuss in section 3.2 are the Gauss's law for the electromagnetic field and the continuity equation. And as you can see, this is the Gauss's law for the magnetic field in the integral form. To simplify the process, we can just check up the analogy of the Gauss's law for the electrical field in integral and differential form and write up to the associated differential form for the Gauss's law for the magnetic field. So as you can see here, to the right, the closed loop, closed surface integral are written as divergence. And to the right is the volume integral. Because for the Gauss's law for the magnetic field, to the right, always zero is always equals to zero because there is no standalone magnetic charge. So the divergence of B must equal to zero at all times. So the Gauss's law for electric and magnetic field are the electrical flux density, the divergence of electrical flux density equals to the electrical charge density, and the divergence of magnetic flux density equals to zeros at all time. And okay, so for any given point, the divergence of magnetic flux density shall be zero at all times. So I can give you an imaginary or an arbitrary magnetic flux density distribution, and I may ask you, is this a legitimate? Legitimate is 什么？合法的、合规的。Is this a legitimate magnetic flux density? To answer this question, you can simply take the divergence of the function of the magnetic field flux density function and check up the result. If the result equals to zero everywhere, then this shall be a legitimate magnetic field magnetic flux density. 所以要检视说一个磁透量密度或者一个磁场强度是不是合法合规的那么它的那个你去检视它的散度必须要在任何地方都是等于0的那原因就在于说我们没有磁核so the net longitudinal differential of the components of B shall equals to 0 at any time because at any time anywhere because there is no standalone magnetic charge. So here is example 3.7 is asking you to check to find out the divergence of vector A, which is vector prescribed in the cylindrical coordinate system. So you need to find out the divergence operation in the cylindrical coordinate system and substitute it with components AR and A phi into the equation and find out the result. And for this example, which you need to do this yourself at home, you can find out that the derivative is minus cosine phi over r to the cube and plus cosine phi over r to the cube. So it equals to 0 for any given r and phi, which satisfies everywhere. Everywhere. The divergence of A is 0 everywhere, even though that the description itself seems a little bit complicated, but the derivative, the divergence of A equals to 0 everywhere. So this is the so-called legitimate magnetic flux density description. And the last thing we'd like to discuss about in section 3.2 is the conservation of a charge in the integral form. And in the differential form, it can be it's referred to as the continuity equation, 连续定理. So we check out the integral form first. That is, the closed loop integral of J equals to the minus of time derivative of volume integral of electrical charge density. So by comparing the integral form with Gauss's law for electric and magnetic field, we can write up the integral form for the conservation of charge shall becomes what? Because to the left is a closed surface integral, so it can be replaced with a divergence operator. And to the right is, it swings to a point, so it becomes the time derivative of electrical charge density. So it's a minus del rho divided by del T. Yeah, all right. So we have equation 3.41, that is, which is known as the continuity equation. So it tells us for a specific point in the space, the divergence of the current density due to the flow of charge at that point shall equals to the time rate of decrease of charge density of the charge density at that point. 所以特定点的电流密度的散度，特定点的电流密度的散度是那一个点的电荷识变率的负值，好不好？所以在记这些式子的时候，请你记得把它的 interpretation 它的解释跟数学式合并在一起看，试着数翻英或者是数翻中，好不好？当你能够看着数学式讲出它的物理意义的时候，我相信你应该对于这一个式子的理解跟掌握可以更进一步。OK， 好，所以这个是。